Hello, everyone. I'm Guohui from Alibaba. Today, I'm going to talk about the work we have been doing on top of SONiC in terms of supporting large-scale operation in our network. OK, Alibaba has been joining SONiC community back in 2017. Since then, we have been an active participant and contributor to the SONiC community, and we have worked on and contributed to TACA's VLAN trunking, SONiC telemetry, as well as warm reboot, and 6dB optimization, a bunch of different features. And we also lead the design discussion on several areas. So internally, we actually also built on top of SONiC with a bunch of different specific features, such as dual uplink support, telemetry, command line interface, BGP enhancement, etc., in order to deploy SONiC in our production environment. So also, I think in last year's OCP, we share some of this work in terms of those deployment support. OK, now we have a bunch of SONiC fleets running in production. Then running a new platform in production is actually not an easy job. There are a lot of different kind of operation tasks we have to do in order to run it well, such as configuration management, monitoring, maintenance, failure recovery, and software upgrade, et cetera, et cetera. But with SONiC as an open platform, we can do a lot of things in different ways to make the things easier to manage and operate. I think this is a good thing, and also this is something we are actually why we choose SONiC. So in today's talk, I'm going to be focused on these 4 aspects in terms of operation support. I think there are also a bunch of other different operation things, but we're just choosing these 4 as an example to show you what we did. OK, configuration management. Traditionally, in our legacy network, I think it's probably a lot of the same thing for a lot of the you guys running with vendor boxes, where the configuration is actually managed mostly based on the command line interface, where when you provision a box, you basically deploy a command line config file, and when you try to update the configuration, you basically need to write a bunch of script to pass the command line, and then do a bunch of different checks. So this screenshot is a little hard to read into, but I mean, it should be fine because I made them up anyway. So this kind of interface is hard to program because you have to basically SSH into the box and then run the command line script and do a lot of different parsing in the system. So it makes the management system a big headache. So using SONiC, we're actually kind of starting to transit from a command line-based interface system to an API-based system to make it easier to program and manage by software. So where the configuration was actually done through a bunch of different gRPC APIs, where the config file is actually organized in JSON format instead of the command line kind of format. OK, not us. So for using the JSON format data, it's actually easy to update any kind of configuration, because now if you want to get, if you want to read and write some of the config file, you just easily do a get and set on some of the keys. And also using the gRPC API, it makes config file interaction much faster, actually reducing the interaction time from seconds to milliseconds. So to support those kind of API-based config file configuration management, we built a GNMI server on top of SONiC to provide a different kind of get, set, and sub APIs on a different set of config attribute. So for the configuration data, we're basically doing something similar to a GNMI model, where we customize the config data structure. It's not a full GNMI data, but we actually basically using choose the part of the config file we actually config attribute we care the most and make them into a GNMI format. And then we build the GNMI server on top of our gRPC interface to provide different kind of APIs. And on the bottom part of the system, we we're using the virtual DB path to abstract the configuration keys from the real implementation, so that when there's any API, when there any kind of we don't have to change the API between our management system and box very often. And then when any kind of, we keep the API fixed, but we can change the implementation of the config on the device. We also covers all the config change and read and write on both DB paths and non-DB paths. So for a lot of the security and reliability reasons, we also set a different whitelist to protect some of the config file attribute, so that to have access control to the config DB. Okay, for the device monitoring, traditionally a lot of our device monitoring was based on the SMP and the syslog, where you do the SMP pulling to the device every couple minutes and to read a bunch of data. But the problem with SMP, I think a lot of people already talk about in the community, is that you have a long monitoring delay, where if you have a problem happen, you probably won't be able to detect it until the next pulling. And the data is actually hard. There are a lot of different legacy code exists in the SMP modules to make it very error prone. And for the syslog monitoring, I think a lot of people have that syslog server to read a syslog from different kind of devices and to pass the tags pounded from the syslog and doing a lot of complicated text analysis to read the data out of the syslog. It's a very noisy data and hard to analyze. Of course, a lot of Windows devices only give you a black box monitoring, where you really, you really don't know what's going on inside the box. The only thing you can see is from some of the syslog error or some of the SMP exceptions. So on SONiC, we do something very differently, where we instrument the SONiC system to build a customized monitoring system inside from the box. So what we did is we built an app watchdog in each of the app containers. So we monitor the process states of each of the individual process, so that if there's any exception or the process hung or exception happens to, for example, the BGP daemon, we'll generate an event and write into the system monitor DB. So we create a separate DB table from the system DB we call monitoring DB. So any process state, exception, or event will be read into that DB. We also set up the syslog filter to capture the syslog from different containers. And we can set a rule to filter a bunch of different important events from the syslog. And then that will translate into a key value event right into the sysmonitor DB. So building on top of the sysmonitor DB, we have a sysmonitor daemon will basically listen to any data right into the sysmonitor DB and apply a bunch of simple analysis or threshold checking to generate important alarms. So that alarm will be streamed out through the gRPC channel we created. I think a lot of people using the gRPC channel in the telemetry. And that event data will be reported to our monitoring and collector. That will be also ding alert to our on-call or the engineers or the operation folks to perform any action, follow-up actions. So this monitoring system is very different from the traditional box monitoring, where it goes through the gRPC channel, which is very fast, and it's doing the real-time push notification instead of periodical pulling. So before, those kind of monitoring pulling were happening at a minutes level, but now this is basically happening at real time. We can get whatever happens on the box, the alert will be generated to the engineer or the operation guys within a couple of seconds. And this monitoring channel will also provide a lot more detailed information about the device. Now we can see the process states of each individual process. Like if anything happened with the TeamD, BGP, or the DB process, or any other process on the box, we'll be able to see that. this is not the box is really not a black box to us anymore. And because the data is actually streamed out through the gRPC channel in event format. So this makes our monitoring system much easier to analyze the event data in very structured format. So it makes our box monitoring and network management system easier for both. Okay. Because we're using gRPC channel very heavily in our configuration management and monitoring systems, so we find a bunch of different kind of system-wide issues on the vanilla SONiC. We also talked with the community quite a lot in terms of the system optimization. One example I'm showing here is about the DB optimization, where we talked to the community for quite a while. Because we're using gRPC channel very heavily, and the gRPC is actually very DB heavy. It's the channel will actually read and write a lot of different data into the DB. In the meantime, different applications is also doing the same thing to the DB. The SONiC system originally only has one DB instance, one Redis DB instance to cover all the different DB tables. We found that in this kind of user scenario, this single instant DB become a system-wide bottleneck in terms of performance and the interference between different kind of components. And then we actually restructured the SONiC to support multiple Redis DB instances so that you can actually separate the read and write path and separate different components into a different DB instance. The way we did it was we basically support a multi-DB configuration at build time. So you can, if you think your system will have different DB, you can actually cover up the DB to have a different DB for monitoring, different DB for ASIC, different DB for instance for the apps, etc. So you can configure the DB, multiple DB instance as a build time, and you can dynamically binding the different DB client to different DB instances. And from our experience, actually separate the DB instance for routing, monitoring, and management, we get very significant performance improvement. We got actually over 50% of a performance improvement on the routing, on the raw installation performance. Okay, device maintenance. This is a very big topic, right? You have to do a lot of maintenance when you see some failure on some port, on some device, or some software issue. I think I'm just using one example to show you what we did with device maintenance. We call it device isolation. I think in a lot of our previous talk, we also shared with you that for a lot of the historical reason, we have a dual uplinks in the rack level, basically, which means for each of our server, we have actually 2 top rack switches. And then we can do failover between the 2 top rack switches using the L3 routing. We share this kind of design also in the OCP last year. Okay, with this dual uplink support, we don't have to do traffic draining, right? I think a lot of the people, if you have only one top rack, if you want to reboot the top rack switch or you kill one box, you basically have to drain the traffic from that rack and migrate to a different rack. With this dual uplink, we don't need to do that. We can do a device isolation where we isolate this one top rack switch, and the traffic can be filled over to another one when you are doing the device maintenance of this one rack. Traditionally, the device isolation was done by if you are isolate one whole box or isolate a bunch of the port from that box, we simply shut down that link, that downlink, and it will trigger a link down event that will trigger the route withdrawal, and also on the servers, the NIC will detect that link down and then do the traffic failover. But there's no control between the server behavior and the routing behavior on top of the top rack switches. So if you look at this 3 event, so between the event 1 and 2 and 3, we can't control the timing. So during that time, when the port is actually offline, we see a lot of the packet loss during the device isolation. But when we're using VendorBox, you can't really control the timing that precisely. Using SONiC, we can actually do a very different thing to control the timing and coordinate between the switch and servers to perform very graceful isolation. So what we did is we customized the protocol on the switch to make it work with the server when we do the device isolation. What we did is actually before you shut down a link, we basically send a link disable signal to the server first. And the server, after the server receives that signal, it will disable the TX of the NIC, which means the server can still receive data, but it's not going to send data out anymore. And then during that time, we can do the NIC failover to migrate the traffic to a different topological switch. And then after that is done, the server will give you an ACK. Will give the ACK to the switch. So now switch knows, OK, now I'm fine to turn on the traffic on top. And then switch will restore the route to the upper layer so that the traffic won't come in to the switch. And then we can shut down the link safely. So with that control, we can avoid the packet loss happening during the device isolation. So this figure shows a very simple test with a 1 TCP flow at different rates from a pair of servers during the device isolation. You can see on the right curve where we used to have thousands of the packet loss during a device isolation, but using the customized protocol we built on top of SONiC, we actually pretty much remove all the packet losses. That's only very little bit, but if we can talk about the details of why we have a little bit offline, but we can pretty much remove almost all the packet loss during the device isolation to make a very graceful device isolation operation. OK. Another important topic for the operation is about the software upgrade, where we have to basically update the software from time to time. I think all the people know SONiC is a container-based system. It's very different from a lot of the vendor boxes. Before, on the vendor boxes, the software upgrade is mostly using the hotfix and code fixes, where you basically a code patch to the OS. On the production network, we actually have thousands of different kind of code patches accumulated over years. It's a big headache to manage. On SONiC, we are doing a modular-based software management, where if we find any problem on one Docker, we'll basically upgrade the image of that Docker, the whole Docker. And so the software management is actually moving from the hotfix, code fix into a package or Docker image-based modular management, which is much easier. And we also built a bunch of different tools to manage the software versions, different Docker image versions on the production network. Of course, we also work with a community on the warm reboot, where during the software upgrade, we don't have to interrupt the traffic. So we're also using the Docker warm reboot, and of course, sometimes the system warm reboot. So with a different way to manage software version is one thing. Another thing is actually how do you verify your software is actually reliable before you actually push into production. That's a very big operation task when you do a software upgrade. So we build what we call SONiC Emulator, basically to try to reproduce the production environment before you do a software upgrade. The thing the build is we build a full virtualized SONiC image, which is not just the SONiC itself. It's also we also virtualize the ASIC behavior. So we actually build a fully virtualized device, including the control plane of a SONiC. Also have the simulated behavior of the ASIC and the SDK and the SI involved. So that device is basically the same device. You can treat it as the software level is basically the same as a real box. except that the faulty behavior is actually going through a behavior model of an ASIC. So using this fully virtualized device, we can actually set up a emulation testbed with real SONiC software, real configuration, plus a virtualized SONiC, virtualized ASIC model, and a virtualized topology, and generate traffic to validate the software upgrade. So this emulator gives us a very powerful tool to perform integration testing and develop an environment in virtualized box. And also we can do the operation rehearsal, where we'll try to do an operation task, like you update the software version on the device, or we update the configuration on the device. We can actually rehearsal the operation from the emulated testbed before you do that, and which make our iteration much faster. We can, of course, using the emulation environment to perform the troubleshooting, like reproduce the issues we found in production. OK, this summarizes the topics we talked today. Here, I want to share a little bit about our lessons we learned while running SONiC in the production. The first thing is actually, I call dangers are in the gray zone. Because as a developer, we always focus on the software we built. We really like our software, so we put a lot of emphasis on the things we built. But problem happens outside your focus. A lot of issues are coming from the platform layer, firmware, or the interop issue between the different hardware and the software interactions. So this is actually a dangerous gray zone. And this is also a tricky issue to deal with in the production environment. So, but we found that the real-time failure detection is a real key to handle those kind of issues, because you can never know, you're never sure you actually don't miss anything, right? So the fast failure detection and the reaction is a key in handle a lot of the gray zone dangers. Another thing is actually, while we are building the API-based configuration system, we found that there are several things it's actually missing in the current SONiC system. One is the configuration validation, where in today's SONiC, we actually don't know whether or not a whole bunch of configuration is actually all correct. If there's any issue, it might fail in the halfway. Another issue is SONiC by design is a loosely decoupled system, where a lot of different components running in a very loosely decoupled architecture. It's very hard to guarantee a strong consistency when there's any configuration update happen. For example, if someone change the configuration very quickly from a software, you really don't know when that configuration actually happened in the ASIC. So this makes it a little bit complicated to interact between the software-based management system and the device. So this area is also the area we actually put our efforts into. The third one is actually software management challenge, because now we have a lot of different Dockers and Docker images. And you may have, on the production environment, you may have different Docker versions on different boxes. And it's very hard to cover the compatibility between all different Docker images. And also, you may have a fragmented software running on thousands of devices, for example, actually even more if you consider Dockers. So this software fragmentation issue is actually is one thing we found in the operation of the large-scale system. And emulation and operation rehearsal make it easier. So I think the emulator we built solved a lot of our problems, but this is also a long-term challenge we need to deal with. So a lot of the works we talked here is actually joint effort with the community. We also work with a lot of different internal teams inside Alibaba for this operation work. For example, our NetOps team and management teams. We, of course, very happy and like to work with the community to build even stronger operation support on top of SONiC. I think there are several different kind of topics we are very interested and look into, such as the failure handling and troubleshooting tool on top of SONiC, and make it more easier to build software-driven management interface on top of SONiC. And also, of course, the system and the network visibility is always a desire for the operators. And this version control and fragmenting the version issue is also something we would like to invest into. With that, well, I'll close the talk, and I'm happy to take questions. Thanks.
About the multi-instance, the Redis DB, I noticed Alibaba upload a document about the cluster for the Redis DB.
Yeah.
Do you guys plan to upstream the multi-instance with Redis DB soon, or the changes?
Actually, we already uploaded the change, right?
You already uploaded?
Just waiting for the approval.
Oh, okay. Okay. Okay.
Yeah, it's a pretty big change, actually. It's kind of refactor the whole things about the DB management.
Okay, cool. Another question is, you mentioned it's bottleneck. Redis DB was the bottleneck. Do you have any quantified information to prove the Redis DB actually is the bottleneck, or? Yeah,
we actually did a talk in one of the community meetings. We presented a bunch of data. We actually did analysis with the raw installation performance and monitoring performance. We found that maybe there's a document in the community. There's a slides, right? Yeah. Yeah.
I believe we have time for this one over here.
So GNMI configuration management is also going to come in April. So that is my first question. So for the GNMI configuration management, GNMI is basically dependent on Yang tree. So do you use any Yang models for your key path? So how is that configuration management done?
So we didn't really using a full Yang model. I mean, we think that the Yang is a little bit too heavy to us in terms of the DC management, configuration management. So we simplified that model. But we plan to using Yang model for some of the configuration validation work. So this is kind of yes or no kind of answer, I think.
So is the GNMI configuration management going to come in April? That was my first question.
Oh, sorry, I actually don't know. I don't think that's in the roadmap right now.
Because we have the get already, but we don't have the set.
Yeah, we're definitely happy to work with whoever. I mean, if the community is interested in the same model, we can actually work with the community for that.
Right.
Yeah.
The gRPC part is already ready. The GNMI part is not on April's release.
I believe we have time for one more.
So yeah, for all the things that you mentioned in your talk, are you upstreaming everything, or is it only a few things that are upstreamed? What's your plan of actually distributing to the or contributing to the community?
So we are happy to work with any, like I think okay. Let me put it this way: for any common component or the technical contribution, we are happy to work with community to contribute to the upstream. But there are some of the work is actually very specific to our topology or our internal settings. Maybe it's kind of hard to generalize everything, but I think this has to go through a discussion between the community and us in terms of how we actually contribute, right?
Right.
But we're definitely open to that, yeah.
Yeah, I saw something called like Ali CLI. I mean, is it something totally specific that you don't plan to contribute?
Well, for example, that device isolation is very specific to our network, right? You have, no? Okay.
But in general, we are talking with all the community members, and Alibaba is willing to open source, but we are taking the common ones for the user in the user space, right? There's some highly customized for their network that we are taking something, not taking everything. Take the common one scenarios that will go to the community. Yeah. Thanks, Guohui.
Yeah. Yeah. Thanks, guys.
Yeah.